Bismillah ar-Rahman ar-Rahim. This is lecture 12 on symmetric matrices. What is special about AX equals lambda X when A is symmetric? There are two facts. A symmetric matrix has only real eigenvalues, and the eigenvectors can be chosen orthonormal so that S, the eigenvector matrix, becomes Q, the orthogonal matrix. Since A is equal to A transpose and A is S lambda S inverse, then A transpose is equal to S inverse transpose lambda S transpose, which is Q inverse transpose lambda Q transpose. And since Q inverse is Q transpose, then A is equal to Q lambda Q transpose. This is the spectral theorem in mathematics. Every symmetric matrix A has the factorization Q lambda Q transpose with real diagonal lambda and orthogonal matrix Q replacing the eigenvector matrix S. This is also the principal axis theorem in geometry and physics, which is an important application of eigenvalues and eigenvectors. So we prove this by example first. Question is to find the lambdas and x's when A is symmetric, which is 1, 2, 2, 4. So calculating A minus lambda I with determinant equal to 0, we get lambda squared minus 5 lambda equals 0. So we have lambda 1 equals 0 and lambda 2 equals 5. Also note that D equals 0, the determinant is 0. So lambda 1 equals 0 is an eigenvalue, and the trace is equal to lambda 1 plus lambda 2, so lambda 2 will be 5. Now the eigenvectors here are x1 equal to 2 minus 1 for lambda equals 0, and x2 equal to 1, 2 for lambda equals 5. They are orthogonal because x1 transpose x2 equals 0, but they are not orthonormal. To make them orthonormal, we divide each vector by its norm, its length, which is root 5. So S becomes Q, which is this. And S inverse is simply Q transpose. So Q transpose times A times Q is equal to lambda, which is 0, 0, 0, 5. Okay. We prove here for any 2 by 2 matrix, if A is equal to A transpose equal to AB, BC, then the eigenvalues are real and the eigenvectors are orthogonal. So if we calculate the determinant of A minus lambda I, we get this, lambda squared minus A plus C, which is the trace, times lambda, plus AC minus B squared, which is the determinant, is equal to 0. This factors into lambda minus lambda 1 times lambda minus lambda 2 equal to 0. The product lambda 1 lambda 2 equals D, which is AC minus B squared, and the sum is lambda 1 plus lambda 2 equals T, which is A plus C. The test for real roots of the quadratic equation ax squared plus bx plus c equals 0 is based on the discriminant b squared minus 4ac greater than 0. Our equation is lambda squared minus t lambda plus d equals 0. So the discriminant is t squared minus 4d, and this is the test for real eigenvalues. So for real eigenvalues, this must be positive, it must not be negative. If we calculate it and expand, we find that it is a minus c squared plus 4b squared, which is greater than 0. So lambda 1 and lambda 2 are real. Now, the fact that eigenvectors are perpendicular can be checked by computing x1 and x2 and their dot products. So from a minus lambda 1I times x1 equal to 0, we get the first eigenvector, x1, which is b minus lambda 1 b and lambda 1 minus A from the first row of the matrix. And for that second eigenvalue, the second eigenvector is the solution of A minus lambda 2I times x2 equals 0. So x2 here will be lambda 2 minus C and B. If we use the second row, we could also use the first row, and we would get B and lambda 2 minus A. The result would be the same if you calculate x1 transpose x2, whether we use this or that, or if we use the x2 calculated based on the first row. The last result would be B to lambda 1 plus lambda 2 minus B times lambda 1 plus lambda 2 equal to 0, okay, which proves that the eigenvectors are orthogonal in general for a symmetric 2 by 2 matrix. Now, A has real eigenvalues and real orthogonal eigenvectors if and only if is A equals A transpose. This is a conclusion. Okay. A proof of this also, if you take the two eigenvalues and the two eigenvectors, then AX equals lambda 1x for the first eigenvector. For the second eigenvector, it is AY equal to lambda 2 times y. If we take the dot product of the first equation with y, okay, we will get AX transpose times y on the left side, and on the right side we will get lambda 1 x transpose times y. Now, if we expand this, it is x transpose times A transpose times y, but A transpose is equal to A because it's symmetric, so it is x transpose AY, but AY is lambda 2 times y, so we get lambda 2 x transpose y on this side, and here we get lambda 1 x transpose y. So if we take this to the other side, it will be lambda 1 minus lambda 2 times x transpose y equal to 0. But since lambda 1 is not equal to lambda 2, then x transpose y must be 0. So eigenvectors corresponding to different eigenvalues are orthogonal when A equals A transpose. Let's take an example. Find the lambdas and x's for the symmetric matrix with trace 0. A is minus 3, 4, 4 plus 3. So the determinant of A minus lambda I is equal to 0, and it is equal to lambda squared minus 25. So we have two roots here, which are lambda 1, 5 and lambda 2 minus 5. Now the eigenvectors will be x1, 1, 2, and x2 will be minus 2, 1. So they are perpendicular. To make them unit vectors, we divide by the norm, which is root 5. So we get q1 and q2, okay, as the columns of q. And then we calculate q transpose, and lambda is 5, 0, 0, minus 5. It's a diagonal matrix, so A is equal to q lambda q transpose. So every 2 by 2 symmetric matrix looks like A equal to q lambda q transpose. So q is x1, x2, lambda 1, lambda 2 times x1 transpose, x2 transpose. Okay. If we expand this, we get lambda 1 times x1, x1 transpose, plus lambda 2, x2, x2 transpose. Notice that x1, x1 transpose is a column times a row, which is not a scalar, it is a matrix. But it is a matrix of rank 1, and it is a projection matrix on the eigenvector direction x1, P1. P2 is the projection matrix on the eigenvector direction x2. So in this example, A factors into two matrices. Okay. And here they are. There are two rank 1 matrices. This is the spectral theorem for symmetric matrices, which says that A is a combination of projection matrices. A equals lambda 1 times projection matrix P1 plus lambda n times the projection matrix Pn, where lambda I is the eigenvalue and Pi is the projection onto the eigenspace I. Now, what if the matrix A is real and its eigenvalues are not real? They are complex. As an example, we take the rotation matrix, which is cosine theta, sine theta, minus sine theta, cosine theta, which rotates a vector in the direction, using the angle theta. So the eigenvalues of A is A minus lambda I, take the determinant equal to 0, and this gives us lambda square minus 2 lambda cosine theta plus 1 equal to 0. So lambda 1, 2 is equal to cosine theta plus minus square root of cosine square theta minus 1, and lambda 1, 2 would be cosine theta plus minus I sine theta. So the eigenvalues are complex, and they are complex conjugates. And if we calculate the eigenvectors, we will find that for lambda 1, x1 is 1i, and for lambda 2 it would be x2 1 minus I, and they are also orthogonal. Okay, now x2 is equal to x1 bar. It is the complex conjugate, and lambda 2 is equal to lambda 1 bar. So for real matrices, complex lambdas and x's come in conjugate pairs. So if we substitute into the equation ax equal to lambda x, okay, for the first eigenvector, multiply matrix A with 1i, and you will find that lambda 1 factors out times x1, and the same thing for the second eigenvector, lambda 2 times 1 minus I. So one of them is ax equal to lambda x, the other is ax bar is equal to lambda bar x bar. Okay, so all symmetric matrices are also diagonalizable. So A equals A transpose is A equal to S lambda S minus 1, or A equal to Q lambda Q transpose when we make the columns of S orthonormal.